Welcome to chapter 11, all about solutions. And so I want to make sure we're all on the same page, do get some of the background information about what solutions are and kind of what makes them special. So if we go back to the very early discussions of what matter is, we know we have the idea of a mixture. And this is a sample of matter with two or more pure substances that can be separated physically. So they can undergo filtration or distillation, something like that. You can separate that mixture in that way. And they're made by mixing two compounds together at different ratios. And so the important aspect about mixtures is that they have variable composition. So compounds always are the same. Water is always two hydrogen atoms and one oxygen atom. It's always going to be the same thing, always has the same properties. But a mixture you can make in different ways. And that's really important because that gives you different sorts of varieties of your mixture, and that lets you control their properties, right? So you can fine tune the properties of a mixture to get whatever you want for whatever application you're looking at. There are two types of mixtures. They are homogeneous and heterogeneous. So the difference between this homogeneous and heterogeneous is where this mixing is happening, right? So mixtures mean you are mixing together different compounds. That means you are mixing together different molecules. And so in a heterogeneous mixture, something like, for example, wet sand, if you were to zoom in at the atomic level, there would be like a cut where there'd be like regions of sand molecules and regions of water molecules. And so this sort of heterogeneity means they're mixed together, and you can have really wet sand or kind of wet sand. It's still variable. But importantly, one of the things that means is that you'll have regions locally of where the atoms are that is only sand. It looks like sand, and other regions that look like water. And so that sort of heterogeneity is going to affect some of the applications as to what we want solutions for. So homogeneous mixtures, where the mixing is at the molecular level. So for example, tea, you have water molecules, you have sugar molecules in there, you have caffeine molecules, you have all sorts of way more types of molecules in that tea. But importantly, they are mixed at the molecular level. It's not like in tea, you have regions of all the caffeine is in the bottom. It is equally distributed throughout the entire mixture. At the top of the glass, bottom, sugar, all that kind of stuff. As long as it's fully dissolved, it's going to be fully distributed within the mixture. And so you can kind of start to see that this is going to be really useful. One of the things that means is that drinking your tea, it will be consistent from the top to the bottom, which is useful in terms of enjoying it. That also has a lot of applicability to, say, a chemical system where you want to set up a mixture to use in a chemical setting. You want it to be the same throughout. You don't want reactions to be happening in different parts of your beaker at different ways. So homogeneous mixtures are more oftentimes called solutions. Solution is just another word for homogeneous mixture. So whenever we're talking about solutions, that does imply mixing is at the molecular level. There is homogeneous solutions does have a bit more of connotation of the idea that one of your substances is dissolved in another. And so what that kind of means is that you have a solute and a solvent. And so here I have an example, kind of little image where I have these greenish crystals, and they're getting dissolved into this water. And so the important thing here is that, when we think about dissolving, the water is called our solvent. So that is doing the dissolving. And we can see that the solution looks like the solvent. The solute, the little green solid crystals, get put into the water and they dissolve. So it looks like they disappear. But what really happens is instead of being big chunks of a bunch of atoms together, molecules together, they're just distributed throughout this at the molecular scale. So that's why you can't see them anymore. Importantly, the phase of the solution, in this case liquid, matches the phase of the solvent. So water was a liquid, the solution is still a liquid. That means the water is the solvent. That's kind of what the idea of dissolving is. You take something from one phase and you get it mixed into the phase of the solvent. Importantly, you still have some properties of the solute. You can see the solution's green now. It's just not solid anymore. And so the phase of the solution always matches the phase of the solvent. It's important to note that solvent and solutions in general don't have to be liquids. So for example, you can put all sorts of things into liquids. So gas, liquids, and solids, you can put them into liquids and make liquid solutions. You can also put, say, gas into gas. So air is a solution. In this case, when you have gas in gas, it's hard to tell what phase. You can't necessarily pick a substance as the solvent based on the phase that it is. Instead, you have to use what you have the most of. So air is mostly nitrogen. About 70% of the molecules in air are nitrogen. So you would say that nitrogen is the solvent for air. And then, oxygen, carbon dioxide, argon, carbon monoxide, all that stuff is dissolved in the nitrogen solvent, making up the solution of air. You can have solids inside of solids. Those get the fancy name of alloy when they're two metals. Whatever you have more of. So for example, liquids and liquids, again, whatever liquid you have more of. So wine is ethanol dissolved in water because it's mostly water still. Generally, we talk a lot more about water as the solvent, but important to note, whenever we do talk about that, these similar ideas apply to any other solvent, all of these concerns. We're going to focus on water because it's the most common solvent, especially in terms of chemical context, but you can have these in other these ideas about solutions still apply to any other solvent. So solutions have some important characteristics. First, the distribution of particles is uniform. That's just another way of saying it's a homogeneous mixture. That mixing is at the molecular level. That's really important for chemical applications because if we're trying to, say, run an experiment in a solution, we want that experiment to be happening evenly throughout the solution. We don't want to worry about where is this reaction happening. We want to have control. And so, generally we want to have low heterogeneity. When you have a heterogeneous mixture, there's heterogeneity. Certain parts have different compositions, and that leads to different properties, and you don't want that to happen. You want to have more control. You want to decrease your variety. So homogeneous solutions are going to be useful for chemistry. Importantly, though, you can make solutions with different compositions for any solvent/solute pair. So you can have really salty water or any kind of salty water. So compounds are important because they have properties, but you can't modify that. When you start making mixtures, making solutions, how salty do you want it to be? Salt is just salty, but you can, get a ton of salt in water or very little, and that will affect the properties of the solution that you can see as well. We'll talk about moving forward towards the end of this chapter. Importantly, though, solutions can be physically separated. This is really important because you can undo this mixing. Molecules in a mixture they interact via intermolecular forces, which we know are much weaker than chemical bonds, so you can undo making a solution. It's not necessarily easy, and importantly, solutions do not separate with time. So if you dissolve salt in water and you just leave it in a beaker, it's going to be there forever. It will stay dissolved. So milk, if we think about milk, quote, going bad, there is fat that is floating around in a liquid, little bits of solid fat that are floating around. They are not dissolved. It is not homogeneous. And instead, over time, those pieces of solid start to collect together and become more and more heterogeneous. And when milk goes bad, it's because you have big chunks of fat that have all collected together. So you may have heard of milk being, quote, homogenized. So they try to make it more homogeneous. You break up those bits of fat, which makes the shelf life longer for the milk because it takes longer to get to all the fat being re-clumped up together. Solutions, importantly, cannot be separated by filtration. This does have some utility. It's mostly kind of a pain. So if you think about the idea of a filter is, you have small molecules, you have basically a net, and you have holes that big chunks can't pass through and smaller things can. So in the case of, say, sand and water, you have these big chunks of sand, lots of molecules together. They're going to be much bigger than the water molecules, so the water can pass through a filter, the sand can't. In a homogeneous mixture, everything is at the molecular level, so you would need some sort of net or filter where some of the holes are big enough that water molecules can pass through, but not other molecules. There are certain applications where you can do this, especially for gas solutions, but for liquid solutions, it's just not worth it to do filtration. Okay, so when we're forming solutions, we do one of the more common types of solutions that we form is when we dissolve in water. We call these solutions aqueous. So once we dissolve something in water, it becomes aqueous. The phase is AQ. Anytime you dissolve in a solvent, the phase is always 2 letters. AQ, aqueous, means water for most solvents. So for example, ethanol, if you dissolve in ethanol, it's just ET. Usually it's the first 2 letters, but 2 letters always does mean it's dissolved. AQ means it's dissolved in water. So why do we dissolve things? And especially in the chemistry lab, we know that forming solutions is good because you can modify properties, but it's also really important for running chemical reactions. We'll talk about this as we move forward, the idea of how chemical reactions happen, but in order for it to happen, molecules have to touch. Okay? And so if we think of the different phases of matter, in the case of, say, a solid, the molecules are all touching each other, but they don't move. In the gas phase, your molecules are freely moving, but they don't touch each other. In the liquid phase, you have molecules that are touching each other and they can freely move around, meaning your different reactant molecules can come into contact with each other. So reactions happen the quickest, most readily in the liquid phase. And so we generally dissolve things in water or liquids in general to perform chemistry. So if we look at, say, a chunk of sugar, in solid sugar, we know all these molecules are jammed in close together. They're not exposed. There's some molecules out on the surface, but most of the molecules are down in the middle of the solid. When they dissolve, the molecules will separate at the molecular level. Now they're moving around. They could interact with other reactants, and importantly, they are open and exposed. They're not protected, so they're open and available for reacting with other things or being tasted, right? Whatever, if it's in a drink, right? That's why sugar goes a bit better in like a liquid than just eating raw sugar. And even then it's dissolving in your mouth. And so those sorts of ideas that these molecules are separated, they're exposed, they can interact with other molecules and, kind of behave in that way, not just in this chunk where these molecules in the middle aren't useful. So they're all out there, get it exposed. That's why we dissolve.
All right, first video down. Welcome to chapter 11. Looking for any questions on participation 9.4. It's going to be due on Friday the 4th. We still have for our weekend assignments, week 2 homework on Saturday over on Blackboard, and then post lab for evaporation and intermolecular forces lab. Encourage you to take a look at those, see if you have any questions. I did get feedback on the post labs for last week, so look at what I said, how to improve your responses to the questions. If you do have any questions about anything, let me know. Otherwise, that's going to do it for this video, but we're just getting started. We're not at the end yet. You got to watch all this set of videos. See you in the next one.